section 6.2. We are taking a step back from the area. Okay? We're taking a step back from the area idea, even though that is the big problem, that is being solved by an integral. The applications we haven't really talked about much, besides, yay, area of stuff that is not geometric, like formulas that you've learned since forever ago. We haven't talked about applications like in motion or related rates or anything else. And we're not doing that even close to right now. But what we also haven't done is figured out what math is going to be involved in solving integrals by hand. Solving, not approximating. Not approximating, solving. What we saw on Friday was the following. Hey, I have a derivative, right? Derivative is f prime of x, and we can say, off the top of our heads, what was the original if the derivative is 5x to the fourth? And we said x to the fifth plus c? What was that for? Constant. We'll talk a little bit more about him in just 1 second. Antiderivative. The main idea is that we're going what? Backwards. Woo. So instead of having a function and deriving him and finding the function that represents the different instantaneous rates of change, we're going to take a function representing the rates of change, take a derivative, and go figure out the original. That's a good way of putting it. But the original from a derivative is also known as the antiderivative. Kind of makes sense, right? Deriving goes this way, anti goes that way. Okay. We saw some notation, yada yada. Here we go. Definition of an antiderivative. We didn't write that on Friday, did we?
No.
I didn't think so. Who are you and why are you here? Go away. Hold on. Technical difficulties. Now we are good to go.
Oh.
Got it. Okay. So, definition of an antiderivative. A function f. Now hold on. Wait a minute. What's this whole capital thing? What's going on? Guys, this notation is great and grand and all good, except when you see an integral, when you see a problem that is an integral, it's not going to necessarily have little arrows saying, hey, he's a derivative. So you're not going to see integral of f prime. You're just going to see integral of, here's a function, take it, use it, integrate it. So even though this is good and us seeing like, hey, it's a derivative, so we're going to go back to the antiderivative, technically you're just going to see a problem. So now we have to call what's inside the integral f of x. You're just going to see a problem, and there's going to be a function in there. And when there's a function in there, well, there's this new capital F just to think of, okay, it is related to that one. How is it related? His derivative, the antiderivative's derivative, is the function in the integral. Let's label some stuff. Ready? First of all, I don't need to label dy dx as differentials. You guys should know that. But we do need to name the thing inside the integral. I shouldn't say the thing, the function. The function inside the integral is the integrand. The integrand is what is in between the integral and the differential. The proper way of writing any integral, the only type of integral that you can actually solve is when you have an integral and a differential and an integrand in the middle. We'll talk more about that in a second as well. And when we want to solve this integral, first of all, solving the differential of y, it's like a 1. It's going to be a variable, but it's a y because it's in terms of y. We saw that a little bit, right? But over here, integral of a function is his antiderivative. We're not really showing primes right here because you're not going to see it. You're just going to see a function. This is, we already said it, forever numbered. Do you label it? 33. Constant of integration. Another way of talking about it is the arbitrary constant. I actually forgot I was going to label it up here. It looks really weird to me, but I think I'm spelling it right. Period 1 said so. Hopefully they're right. Arbitrary, right?
Yeah.
Good. And then this one, we already talked about it, and it's the definition, right? But just to make sure you're clear. That's the antiderivative. And y, we could say, is the original. Either way. Quick.
Is the c part of the antiderivative or
Technically, yes, but we give them a snazzy name so that we realize that you're going to be looking at the integrand and getting a specific antiderivative. We kind of talk about him separately because he goes on the end of any indefinite integral. Does that kind of make sense? So he's not unique necessarily to a certain integrand. Okay. Coming back, constant of integration, y to b plus c. We talked about this on Friday. Let's see if you still remember. Question, first of all, give me an antiderivative. I'm going to label it capital F of x. I'm going to name it 1. Give me an antiderivative of 4x cubed. X to the fourth, good. Someone give me another one. Be more creative. Plus 5, got it. Be more creative.
A million.
Okay, that's one way of, okay, there we go. Be different.
Pi.
Ooh.
Got it.
Ooh, even more exciting. Okay. Long story short, I can keep on going. I'm going to stop. Why? We get the point. Graphically, what could all of these be described by in relationship to the original? I shouldn't say the original. To the first one that we wrote down. Why? The y-intercepts are different. Graphically, we would call them, are they changing, like dilating? No. Reflecting? No, they're just shifts. And what kind of shifts? Just vertical shifts, because it's not x minus 2 to the fourth, it's just x to the fourth plus a constant. So we call this whole family that have the exact same, or will have the exact same shape, but different intercepts, if they have intercepts, I guess I should say that. Different positions, but the exact same behavior. A family of antiderivatives. Family of antiderivatives, why? Because we have the arbitrary or the ambiguous constant, the constant of integration. That's whenever we have an indefinite integral, which means an integral without bounds. That's why we're taking a step away from the area, because as you guys were doing homework number 31, they all had bounds. And so their answers, if you were finding or even if you were approximating, they weren't general, they didn't have variables, they had numbers, right? They equaled numbers. But indefinite integrals, kind of like derivatives, slope of tangent lines, okay, cool, that's the idea. Let's take limits of slopes of secant lines and try to find numbers, okay, cool. Let's learn how to find derivatives. Wait, f prime of x equals, they're equations, they're not actual slopes. Well, they stand for slopes, kind of what we're doing here. An integral finds the area between a function and the horizontal axis if it's dx. If it's dy, it's the other. We can approximate using rectangles and trapezoids, and if it's a geometric shape, we can actually find it. Cool. If it has bounds, there's a number. Without bounds, it's an antiderivative. So if I was to give you another example, let's make it exciting. What if I was to say something like y is equal to the integral of, okay, not too exciting. Let's just do x to the fourth. Okay, what would you guys say? It doesn't perfectly fit a rule, but we can still maybe figure it out. Come on, some of you can. X to the has to be x to the 5, because the 5 comes down and then I subtract 1, it's the 4. But when the 5 comes down, ruh-roh, he's not there, so what must be waiting for him? Got it, plus c. So if I have x to the 5th plus c, x to the 5th looks kind of like a cubic, just a little bit skinnier. A lot skinnier. Anyway, all the different plus c's, now guys, they're infinite, so I'm not even pretending that I can draw them all right now, right? But they're all going to have the exact same shape. There's going to be translations of each other. So that's the family of antiderivatives. Now, what is the only way that I could possibly figure out a specific one? The only way I can possibly figure out a specific one is if they give me a specific point. Because if they give me a specific point that must be on the antiderivative, then there's only one that's going to go through that point. And that's where this note comes in at the bottom that you might be writing right now. You can only find C, aka I can only define it to be one specific one when given a point. And I'm going to label it because we're going to be plugging that point in, that x, y in to find the C. And that's only when they give it to us. Sometimes it's just going to be the general antiderivative, which stands for the whole family. One more random note kind of to put in here. We'll talk more about them next chapter. Or next section. Whatever, chapter 6b, that's what I'm talking about. After the next test. But derivatives and integrals are inverses of each other. Meaning, if you take the derivative of an integral, generally, take a derivative of an integral, it just gets you back to the original. If you take a derivative of an antiderivative, it's going to get you back to the original. I shouldn't say the original. Derivative of an integral equals the integrand. Derivative of the antiderivative equals the integrand. They undo each other. They undo each other. If one's forwards and one's backwards, put them together and they butt at each other. Couple more seconds. We good? Now, before I go to the next page, a couple of you guys are still writing. Some of you up to this point are like, great, this is going to be so much fun. So basically I have to look at an integral and then like in my head try to do this weird contortion thing and see if I can figure out exactly where it came from. And if I don't see it, I won't get it. And if I don't get it, I'm going to fail. And some of you are like, psh, got it. There are rules. And this is the beginning of them. Okay, there are rules. This is the beginning of them. We are going to write them in our notes partially. I want to give you the whole thing though and not make you write them in your notes. I think that's 6, I'm not sure. Part of this is going to be a forever card that we're going to mark in just a second. There are rules. I did tell you guys about that big old book Dr. Teague used to have, right? Yeah. And how integration formulas, there's that many of them and it's still not enough because some can't possibly be integrated by hand. Yeah. But that does not mean that there aren't foundational rules that we do need to know and that will help us in approaching every and any integral. Up to this point, I've pretty much been only giving you guys powers, right? Mm-hmm. Pretty much, I think, right? X to the 4th, x to the 5th, 3x squared, etc., etc., etc. I forgot that last time I taped it was quiet. I think this has turned out. But there are more than that. Kiddos, on your handout, first of all, everybody get one? Yeah. Okay. Are there just powers on there? No. What else is on there? Well, first of all, what's on this side? Derivatives, right? Derivative rules that we should already know, and this isn't even all of them, right? So this isn't all the integration ones either. But here's all the derivatives, and here's the corresponding integration rules. Question, which one, can you find which one, count down, which integration formula have I been using the most? Second one, a little bit.
Third one.
Third one, not really. Fifth one. Why? Because the fifth one is what we call, and if I were you, I'd write it in right now, the power rule of integration. Wait, that doesn't look like the power rule. It is the power rule, but backwards. Why? The power rule for derivatives says bring down the constant, subtract one. Integration says add one and divide by the constant that's going to come down when you derive. Plus C, of course. All the basic rules are founded on the main idea that we've already written down. You don't necessarily need to write this again. All the basic rules are founded on, if I take the derivative of an integral equals a function, integral of a derivative equals a function. If you know when you take the derivative of c equals 0, then the integral of 0 should equal c. It's just going to be going backwards, right? But you have these funny ones like power rules where it's like, okay, I know the power rule. Hopefully. I know the power rule, but backwards, wait, okay, hold on. power rule deriving takes one away, so then it must be one higher than I have right now if it is the derivative, but then when it comes down, that'll cancel out. Here's another one. Does anyone else see one that's confusing? Hold on, let me ask you. Is there another one that looks confusing? Where you're like, wait a minute, what? Maybe having to do with signs, S-I-G-N-S, or S-I-N-E-S, literally. Is anything funny about this one? Why is there a negative? Okay, pourquoi? How come? The derivative of cosine should equal negative sign. But this is just the integral of positive sign. So positive sign, well, for it to be positive, well, first of all, for it to be sine, it had to come from cosine. But for it to be positive, there must have been a negative. Another way of thinking about it is, the integration rule is a negative, but I can't just like magically change, oh, but if I make a negative negative, that's a positive. So I can say it's going to be negative, the integral of negative sine, negative cosine. With integrals, there are going to be a couple different ways for us to think about them. I'm going to try and cover them all without confusing you by the different ways of thinking about it. So I might be more structured than some of you want me to be. You might tune me out at times, and that's okay. I might be more structured just to get us a good foundation, and then we might start taking shortcuts as we get more familiar with them. Guys, let's go ahead and highlight the whole right side. That is forever number 34. Forever number 34. Now, can you make columns on your forever cards and not just have like formula, 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 I ran out, oh well. I would. Some of these are small, you can write formulas. We saw with Riemann sums how you can take a constant out. And if an integral is a Riemann sum, I can take a constant out and then take the integral and get it. Same thing here, that's what's going on. We saw with Riemann sums, you can go ahead and split them up, plus or minus, right? What do you not see? I don't see any products, and I don't see any quotients. It's gonna get to be an adventure eventually. Okay. You ready? Ooh, let's do some basic ones. And then we'll get more exciting. If I were you, I would put this, maybe fold it and put it in your notes. Maybe copy it in your notes, maybe just copy it in your forever card. Maybe put it in your binder. If you're going to put it in your binder, though, I would copy it in your notes, or else you won't have something in your notes to go back and reference. And what are our notes supposed to be? Yeah, it's like our guide, right? Okay. Here are the okay. Let's see if I have numbers on these first. You're gonna mess me up? Nope, I don't. Okay. Number 1. We'll start easy. Someone tell me something that I can use to solve this integral. Don't go straight to an answer. I don't want to hear the answer. Power rule. Okay. What about the 5? 5 fourths? Well, I was thinking this first, actually, just in case. Because a few of us kind of got lost in the whole constancy thing with derivatives. I want to make sure we don't get lost with the integrals, okay? Can the 5 just come out and I ignore him till later? My ones who don't like constants with derivatives and you like to do quotient rule a lot. Can I just pull the constant out and say I'll work with you later?
Yeah.
Good. Now, x cubed, what can I do with them? You guys already told me. So then, Jezreel, you already said it. What's my answer going to be?
5 fourths.
Mm-hmm. Every time you solve an integral, what should you be able to do to make sure you got it?
Go back.
Take the derivative. So then the derivative, bring down the 4. The 4's cancel. 5x cubed plus c. Wait, no, not plus c, because the derivative would be 0. So bring down the 4. Shoop, shoop. C's already gone. 5x cubed. Got it done. Let's get more exciting. First of all, any questions? What if I gave you the integral of the cubed root of x squared? Now what? It's not 0. It's not a constant. It's not a constant times a function. There's no addition or subtraction going on. There's no trig. What rule must it be? How can I see what? There's a radical.
2/3.
2/3 is the exponent, right? So then power rule. What do? Take away 1. No, that's deriving.
Add 1.
Add 1. So add 1. Wait. What should I add instead of 1?
3.
Maybe 3 over 3?
Okay.
Maybe 3 over 3? And then what do I need to do? Solve? Solve how? So I'm going to add 1. Now this is going to be really confusing if I write it like this, right? Divided by 2/3 plus 1. What's better? Instead of 1, 3 over 3. When I add 3 over 3 to 2 over 3, I get x to the 5/3. But hold on, if I bring him down, he needs to go away. So I need what weighting for him?
3/5.
Wait, maybe that was too fast. So what's the in between? X to the 5/3 divided by, that's power rule, right? Right? Up for integration.
Oh, yeah.
So add 1, divide by, when I bring it down it cancels, but what's it going to look like if I'm trying to simplify? Multiply by the reciprocal. So let's try this one. What if I was to give you go. Everyone you're going to see is going to have a strategy. There's going to be some rule you can apply. There is no guessing. Bless you. Bless you. Look back at number 2 if you're stuck on number 3. How many of you guys put together the pieces and said, hey, if he's in the denominator, I can just make him a negative exponent and just use
I did that. I did it.
maybe after ignoring the 7 for a second. Questions?
No.
So now what? Plus 1, right? Hold on, the 7's chilling. Plus 1, well, x to the negative 1/2 plus 2 over 2. 1/2, and then I divide by 1/2, which is the same thing as multiplying by the reciprocal. Just a second, that might have been too fast, so then add 1, x to the 1/2, divide by 1/2 plus c. Then I say, hey, that's the same thing as multiply by the reciprocal. Now, quick hint. This is actually pretty similar to derivatives. Guys, remember when you had to struggle through simplifying?
Yeah.
If it started with a radical, what's what's the answer probably going to have? A radical, not a 1/2. Probably. Okay. Questions? Ready for another one? No fun. What if I was to give you? Hold on. Wait, pause. Let me stretch your brains before you leave. Where is he?
I don't have it.
Because he's not on there. If only we knew our trig properties, we might be able to answer a little better. Bye, cool kids. See you later. Tomorrow, we're going to practice. It's going to get exciting. Homework is due for this section on Wednesday. There's an integration competition at the end of tomorrow. Money?
We're dancing, right?
It's only on the billionaire, so.
Yeah, I need to go to college.
Touche.
You'll win, but we won't.
If you ever
Exactly. Kenny has my back. Right, Kenny? Hush up.
Still have parents supporting you.
No.
You're welcome to come,
Saving
Cass.
it.
I told her, I invited her.
Yeah.
Sorry,
It's okay.
She said no, but I'm done. I'm done. James and I are done. I'm down. Danny?
Are you guys going to college tomorrow or Whittier?
I'm going to Whittier.
Going to Whittier?
You got it, Kenny? I went really hard, really fast. This one isn't on the sheet, right? You can look. Is it on the sheet?
Tangent.
Squared? Nope. Why? Because no rule, there is no derivative rule for something that equals tangent squared, for a derivative that equals tangent squared. But if you remember the rule, you know now?
I got up to here.
So I was able to substitute. Now look at rules. Secant squared. What has a derivative that equals secant squared? Tangent. So integral of secant squared is tangent. Integral of 1 is 1 times x, but with a minus plus. Don't worry, we'll practice lots more times.
Wait, constant for x?
No, because 1. K is like 1, 2, 3, 10, 100. K is number. Does that make sense, kind of? So number 1, what has, double check. Derivative of tangent, secant squared. Derivative of x, 1 with minus in between. Derivative of constant, 0. Perfect. I went really hard, really fast. It's because we did some easy ones for people who had done integrals before, so I thought I would trick them. I tried to trick them before they left.
Miss D.
Yeah, then.
So for like number 1, you would basically just add the exponent by 1, and then